So today we're going to work on exponential functions. This will be, I believe it's 6.3 is where this is going to be. So exponential functions, like I said, this is a really interesting topic. Wish we had more time to explore these, but they're used in a lot of applications in math. When it comes to finance, these functions are very, very powerful because one of the things involving financing is time. As I say, time is money. And when it comes to investing, that's where one of the critical pieces is people want to make money quickly over time. So anyway, I digress a little bit. As we move forward, though, I do want to kind of mention a couple of laws of exponents here. So we have what's first, one of the most common ones is what's called the product rule. The product rule, notice how we have the same bases, base A, and if you have the same bases multiplied, what you can do to simplify it is simply add the exponents together. So the base stays the same, and all you have to do is add the exponents together. So if I have a problem like 2 to the third times 2 to the fourth, we can simplify that by actually just simply keeping the base the same and adding the exponents, and write that as 2 to the seventh, and that would be considered simplified. Sometimes you don't have to work it all the way out into an actual number, just something that can be used as an equivalency. So if I have x to the third times x to the fifth, we can add those exponents together, keep the base the same, and this will be x to the power of 2. Another interesting rule is what's called the power rule. The power rule is when you have a, which is the base raised to a power, but then it's raised to another power. So if you have a power raised to a power, the shortcut is to simplify that. All you have to do is multiply the exponents together, n times m. So if I have like 3 to the fourth raised to the power of 2, using the power rule, I can rewrite that as 3 to the power of 8. Similarly, if I have x to the third squared, or x cubed squared, if you will, notice how we have a power raised to a power. We can write that as x to the sixth power, since we would multiply those exponents together, and 3 times 2 does equal 6. Other rules to kind of mention, if we have a times b to the nth power, we can bring this n through the parentheses and go to each one of the individual pieces. So that's the same thing as a to the n times b to the n. Another thing is, if you raise 1 to an exponent, it's still going to be 1. And we also talked about negative exponents. So if you have a to the negative n, that just kind of means to take the reciprocal. So it's going to be 1 over a to the n. Sometimes it's also written as 1 over a in parentheses raised to the n. So those are equivalent. And we have mentioned this many times, that anything to the 0 power is, of course, 1. So let's move into the definition of an exponential function. Our first area we're going to start to deal with is the graphing. So we're going to be focusing on what's called the parent function to start with. And then remember, with graphing, we get into these transformations. So understanding the parent graph helps us do these transformations. So if I have the function f of x equals a to the x, where a is the base raised to the power of x, notice that x is actually our domain. Our variable is actually an exponent. So here we're saying a is greater than 1. So most commonly you'll be seeing a as a base 2 or a base 3 or a base 4. We don't use too many other numbers besides that at this point. So as we move forward, this again is defined as the exponential function is a to the power of x, where a is going to be some number. Some properties of its graph. So we're going to have these 6 properties that we're going to explore. So the first property, the order pair 0, 1, and is going to be the initial point to plot. And also we're going to graph 1 where we use a as the y value, and -1, and use the reciprocal of the base, so 1 over a. So for instance, if I look at this example down here that I have, if I have y equals 2 to the x, notice how we said, 0, 1 was an ordered pair. We said 1a was an ordered pair, and we said 1 or negative 1, 1 over a is an ordered pair. So based on that knowledge, we can go. So if I put 0 in, notice that you would have 2 to the 0. 2 to the 0 would be indeed 1. So notice how 0, 1 does exist. If I pick x to be 1, notice how I have 2 to the power of 1. Well, that's just going to be that base 2. So that's where that 1a comes in. The base just stays there. And then if I use negative 1, so if I do 2 to the negative 1, that means to take the reciprocal of the 2, which turns it into a 1/2. So negative 1 gave us this 1/2. So that's what they mean by 0, 1, and then 1a and negative 1, 1 over a, where 1 over a represents the reciprocal of the base. Some other things to pick up on in our properties is what's called end behavior. As x approaches infinity, what is y doing? As x is approaching infinity, what is y doing? So let's look at, I'm going to do x approaches infinity first. So as far as end behavior goes, let's go ahead and graph these 3 points too. 0, 1 would be here, 1, 2 would be here, and negative 1, 1/2 is not too hard to graph. So we have that kind of going on. So we have that going on. What we want to know is what's going on to the far left, what's going on to the far right. I'm actually going to start with x going to the far right to start with. So as x is getting larger, the question is what is y doing? What's y approaching? So if I do like 2 to the 3rd power, that's going to give us 8. And also, where are I getting off of our graph at that point? 2 to the 4th would be like 16. So what we're kind of seeing is the y values are just getting larger as the x values increase. In other words, they're actually going to go extremely large. In other words, they're going to be approaching infinity. So as far as behavior goes, as I go to the right, the graph should be going up. It's getting larger. Now the question is what's happening when I go left? As x approaches negative infinity, as I go to the left, what's y doing? So if I pick like 2 to the negative 2, notice how that would give us, 1 over 2 squared. In other words, that would be 1/4. So notice how I get a fraction that's pretty small. 2 to the negative 3 would be like 1/8. So what we're kind of seeing is these values here are getting close to 0. So what we're picking up on is as x is going left, the y values are approaching a specific value. They're approaching 0. So that becomes what we call a boundary or an asymptote. So as we create our graph here, let's see if we can make a boundary line. We're going to just use another color here. So the x-axis becomes a boundary line. I'm going to use a color there to kind of bring that out a little bit. And so then if we actually create the graph, so the graph, it starts out low on the x-axis, and then it kind of starts to bend, and then it starts to take off going towards infinity. So the graph would kind of take on that look there. That would be a typical graph of an exponential function where the base is above 1. So some things to pick up on in our properties again is, as I said, the end behavior as x approaches negative infinity, the y values are actually getting closer to 0. And as x is approaching infinity, in other words, as x's are going to the right, the y values are going up. In other words, they're approaching infinity. Notice the graph, there isn't any x-intercepts, but there was a y-intercept of 0, 1. And the horizontal, the x-axis was the horizontal asymptote. In other words, y equals 0 would be that boundary. So if we look at the graph there, notice how again, the graph does not touch the x-axis, so there's not any x-intercepts. It does touch the y-axis at 1, so there is that y-intercept at 0, 1. And also how again, since it doesn't touch that x-axis, that's a horizontal asymptote, which its equation would be y equals 0. Some other properties that we're picking up on is the domain, there is not a domain restriction. It's all real numbers, but also the range is above the x-axis, so the range would actually be y is greater than 0. So if we look at that graph, you can kind of see that the left boundary is an arrow, the right boundary is an arrow. So there aren't any domain restrictions. You can put any value for x in that you want and you'll get an answer out. But when you do put values in for x, all your values are going to be greater than 0. So your range will end up being then dependent upon those domain values, but they're all going to be above the x-axis or greater than 0. There's nothing in below the x-axis there. So we mentioned that. And then when it comes to the parent function, it's going to be an increasing function. It's also going to be a one-to-one function. So if you look at the graph, where again, this is considered our parent function, no transformations are happening yet. Notice how from left to right, it is going in an upward direction. So that's described as an increasing function. So again, most graphs, when you talk about behavior, you're kind of looking from left to right as well for increasing or decreasing. And also it does pass the horizontal line test. So it is a one-to-one function, which is important as we move into the next section. The exponential function can also have a value of a where it's between 0 and 1. So what I mean by that is we're talking about a fraction between 0 and 1, and the most common fraction is the 1/2. So if we look at the function f of x equals 1/2 to the x, let's observe its behavior as a parent function. What's going on with it? So what it says here is, again, those points again are going to be 0, 1, 1 over a, and negative 1 over a, which again is the reciprocal or flip. So if I look at this equation, notice how we have the parent function is this 1/2 x. So if I look at its ordered pairs, so the second view is always a table. So this is the equation, now a table. So if I put 0 in, notice again, 1/2 to the 0, anything to the 0 power would be 1. So that's that 0, 1 that we always talk about. That's going to be a point to start with in the parent function. If we put 1 in, 1/2 to the power 1 is still just going to be 1/2. So the base does not change. That 1/2 stays the same. So 1, 1/2. But if I put a negative 1 in, notice that 1/2 to the negative 1 means to flip it, which becomes 2. 2 over 1 or 2. So that would be our 3 critical points. So notice how now we have 0, 1 again, but now we have 1, 1/2, and we have negative 1, 2 would be the 3 critical points. As far as behavior goes, you kind of see that this graph is kind of doing just the opposite of the other one. It looks like it's finishing high on the left side and finishing low on the right side. So it looks like it's having that kind of behavior. So what we're picking up on again is the graph is again approaching this x-axis, but notice how this time it's kind of flipped. As x's are going left, the y's are going up or going to infinity. As the x's are going right, the y values are now approaching 0. So as far as in behavior goes, we're actually seeing as x goes to the, let me change that to another color there. As x is going towards negative infinity, we're now seeing that the y values are approaching infinity. They're getting larger now. And as x's are going to infinity, as the x is going to the right, we're now seeing that the y's are getting closer and closer to 0. So again, we're seeing that boundary line going on there. Notice again, this doesn't have any x-intercepts, and the y-intercept is still 0, 1. The x-axis is the horizontal axis again. It's the horizontal asymptote. And notice how it's going to be y equals 0. And notice how the domain and range are still the same as well. The only difference is this function is actually a decreasing function, and it's also considered one-to-one. So again, if you look at the graph, again, it doesn't touch the x-axis, so there's not any x-intercepts. The y-intercept is here at 0, 1. And as you go from left to right, you kind of see that it does decrease. And notice again, the domain, there's not any domain restrictions, and the range is above the x-axis. In other words, y is greater than 0. So we all see that. And notice how, again, it does pass the horizontal line test. So all those are properties of this function. So if you can kind of get some of that to memory, it makes the graphing a little bit easier. So we're going to graph functions, and we're going to use these transformations. So we're going to be using transformations. Now remember, outside affects the y values, and remember, you just follow the order of operations. And the inside that affects the x values. So follow the order of operations, but you have to do all that thinking backwards. So if we look at this problem, we have f of x equals 2x plus 3 minus 4. To graph this, the first idea is just identifying what the parent function is without all the transformations going on. So she recognized that y equals 2x is the parent function without anything going on. So as far as that goes, 0, 1 was an important point. 1 gave me 2, and -1 gave me this 1/2. That's the parent function. So when I graph this function, all I have to is identify what's happening to the x and y values. Well, the -4 is the thing we kind of notice first. That's going to affect the y values. And since it's a -4, that does affect it as you see it. We're going the y values are all going to shift down 4. So we're going to lose 4 on all the y values. So 1 minus 4 is going to be a -3. 2 minus 4 would be a -2. 1/2 take away 4 would be a -3.5 or a -3.5. When it comes to the x values, this +3, notice how it's actually the inside now. It's affecting it this way. This +3 is considered inside. And since that's inside, that +3 means you affect the x values backwards. So that should mean all your x values are now moving to the left 3. So that 0 now becomes a -3. 1 take away 3 becomes a -2. And -1 take away 3 would be a -4. So those become your new ordered pairs. So -3, -3, -2, -2, and -4, -3.5. That'd be your 3 critical points. So notice that the x-axis is no longer our boundary. Our boundary actually has moved along with the vertical shift. Since the y value shifted down 4, the boundary has to shift down 4 as well. So my horizontal asymptote is actually now at this y equals -4. That's now our boundary. So when I graph my function now, all I got to do is kind of remember that it's going to kind of be bounded by that asymptote, and then it's just going to take off towards infinity, and it's just going to kind of start doing that. So it's going to be that look. So it should look just like 2 to the x function, except it's been shifted left 3 and down 4. So there's our equation, there's our table, and there's our graph that we can generate. So if we want to try to graph f of x equals 3 times 2 to the -x, the first thing again is identifying our parent function. What is our parent function? So notice that if we take away the transformations, we strip it all away, we should see we just have y equals 2 to the x as our parent function again. So again, as far as ordered pairs go, 0, 1 is an ordered pair, 1, 2 is an ordered pair, and -1, 1/2 is an ordered pair. So when I graph my new function, including the transformations, the 3 is on the outside, so that's going to actually be a stretch of the y values since it's multiplied to the parent function. That's going to be a vertical stretch. So I just multiply the y values by that 3 to create my vertical stretch. So 1 times 3 is 3, 2 times 3 is 6, 1/2 times 3 would be 3/2, or we'd call that 1.5. As far as the x values go, the negative is on the inside, so that's going to actually affect the x values. So that's going to be a reflection across the y-axis. So the x values should all flip over there. So 0 doesn't change, but the 1 is going to change to negative, and the -1 is going to change to a positive. So when I graph this, notice how we have 0, 3 as an ordered pair. That's that stretch. -1, 6. And 1, 1.5. Again, there's that stretch again that we have going on there. So notice how the graph, it's going to now be bounded again by the x-axis since there's not a vertical movement. There's just a horizontal reflection and a vertical stretch. So that does not affect the positioning. It just affects its direction and stretching. So notice how this graph now, it's going to be high on this side. Let me put that back in green again. So it's going to start at high over here. It's going to come down. It's going to pass those 3 points. And then the x-axis just becomes a boundary. So now it's going to kind of take on that look. So notice how, if I look at the x graph, the 3 made these values all move up vertically. So if you multiply these all by 3, so 1 times 3 would be 3. The graph would be there. If I do that, okay. So this point here, if I multiply by 3, would turn into that. And then you'd multiply that point by 3, it would be 6. And then you have to multiply this point by 3, and that would be 1.5. And then that negative number, that negative x, if you will. So then that negative is going to make the graph reflect across the y-axis. So notice that from there, these points are now reflected. This now point goes over here, and this point stays where it is, and this point gets reflected over here. And notice that the behavior gets reflected as well. So it's going to finish high on the left side and finish low over here. And you can kind of see that happening with respect to the original parent function, that it's been stretched and reflected across the y-axis. So that's all that's really happening there. See if I can find my spot again down here. So if I want to graph this function here, notice that our parent function here is going to be the y equals 1/2 to the x. So based on our knowledge of this function, we know that 0, 1 was an ordered pair. When 1 went in, 1/2 was the output value. And when -1 it went in, that reciprocated it, and that became a 2. So that would be our ordered pairs of the parent function that we're using. And then in graphing our new function, the only thing I'm seeing is this -2 on the outside. There's nothing really affecting the x values at all. So there's just this vertical shift of -2. So the x values actually stay the same, 0, 1, and -1. But I have to shift all my y values down too. So 1 take away 2 would be -1. 1/2 take away 2 would be -1.5. And 2 take away 2 would be 0. So that would be my new ordered pairs in graphing this function. So 0, -1. Let me get a little bit more of the graph here. 1, -1.5. And -1, 0. So notice how it really kind of still mirrors the original parent function, except now, let me try that again. My horizontal asymptote has actually been moved down to. So notice how the vertical shift will affect where the asymptote is. So it's now going to be at y equals -2 instead of being y equals 0. So from there, you can kind of see that the graph itself, it's just going to be kind of like the original function, except just been moved down. So it kind of starts out high and finishes going close to the boundary line, the asymptote. So that should be what the graph is. So it should look just like 1/2 x up here. Let's see where I can find that one at. So notice how it's that graph there, but everything's just been shifted down to. So this point went to, that was how this point went from here down to -1, 0, 0, 1, dropped down 2, and went down to -1, and then this point dropped down 2, so it'd be -1.5. And the asymptote would have dropped down 2 as well, and would have been across there. So you kind of see that this kind of roughs it out there like so. So we have the same graph just shifted down 2. So let's look at another one here. I think this is the last one. Yeah. So one more graph here like this. So here again, the parent function again is going to be the 1/2 x. Oops, get back to my other color again. So y equals, again, 1/2 x is going to be my parent function. We'll write that word parent in there. So again, if I understand the order pairs for the parent function, I can generate the graph of the new function. So remember, 0, 1 is always an order pair. 1 went in, 1/2 came out. -1 went in, and I have to flip the 1/2, and it becomes a 2. So those are the order pairs that I'm using. Now, if I can apply the transformations, the -3, this would be considered inside the function. So that means we're going to be affecting the x values. And since it's -3, that means we're going to be adding 3 to all the x values. So that's going to be a 3. 1 plus 3 is 4. And -1 plus 3 would be 2. So from there, there's no shifting of the y values, but there is a reflection and a stretch. So I'm going to be multiplying the y values by -4. So 1 times -4 would be -4. 1/2 times -4 would be -2. And 2 times -4 would be a -8. So that would be my order pairs to generate my transformation. And since there's not a vertical shift anywhere, the asymptote should still be on the x-axis. So 3, -4 would be an ordered pair. 4, -2, and 2, -8. And we kind of see this graph is going to kind of come up through here, start low, and kind of finish approaching the x-axis. So it kind of takes on that look there. So notice how that -4 made it flip across the x-axis and stretch it as well. And the 3 just made the graph move to the right 3. And that's our new graph. In exponential functions, we can't go on without talking about the special number e. So when we get into exponential functions, there's this expression that appears, this 1 plus 1 over n raised to the n. It happens really when we start to get into compounding money and things like that. We may see some applications later on that develops that a little bit. But what this happens is as this expression here approaches infinity, what we understand is this actually approaches a specific value. This thing actually approaches e. So when I put values in for n, the answer of this expression gets closer and closer to this number, 2.71828, and then it keeps going on just like pi does. So there's not an exact value for e. There's only an approximate value for e. Therefore, we just use the letter e to replace that instead of trying to write that big old long number. So it's just a special number, and it's used in a lot of applications involving exponentials. So if I want to graph this function here, remember e, for my purposes, is approximately 2.7. For me personally, we don't need all that when I'm graphing it, just a general estimation here. So when I make my little table, this is going to be my parent function. And 0, 1, 1 would be e, which is about 2.7. And -1 would be 1 over e. And that would be, like 1 over 2.7, or we'd say that's about 1/3. So that gives me a little bit of an idea about where to graph that point. So if I want to graph this exponential function, 0, 1 still becomes a critical point. 1e would be about 1, 2.7. It would be about here. And negative 1 over e would be about where 1/3 is. So it'd be about here. So this graph really kind of does the same thing as the first graph we did with the base 2. This base is just a little bit different, but it's just a crazy number, but it's still above 1. So notice how this graph starts along the x-axis and then kind of bounds up and starts to take off towards infinity. So as we go to the left, it gets closer and closer to the x-axis. As we go to the right, it's increasing and going towards infinity. And that would be the graph of that. On your graphing calculator, you should see a button on your graphing calculator, the LN button. And right above it, you see this e to the x. So if you use e to the 1 on your graphing calculator, that'll give you approximately the value of e, this 2.71828. It'll give you something like that, and it'll keep on going. So that's how we actually put 8 or e into the calculator, is right above this ln symbol. There's this e to the x, and I can change the x to 1 and put that into our calculator. So you can try that, see if you can get that to work. So the last thing we get into is what we call solving exponential equations. These look kind of intimidating, but there's just really just a little bit of manipulating, and we can make these things rather easy. So one of the things that comes into play, if the bases are the same, then the exponents can be set equal to each other and solve for x. So if we have a to the u equals a to the v, if the bases are the same, since they're both a, then what I can do is just simply say u is equal to v. So we have that kind of going on. So if I want to solve this equation for x, if you will, find the unknown, what we could pick up on is I don't have the same bases. I really can't change the base 2 because that's basically about as easy as you can get. But 16 can be changed using exponents. We should recognize that 2 is a good number for 16 because if I raise 2 to the 4th power, that's the same thing as 16. So using some understanding of exponents, I can rewrite that as 2 to the 4th. So we can go in that direction. And since the bases are the same, I can just set the exponents equal to each other. And I can solve for x. So if I divide this side by -1, if I divide that side by -1, so in other words, the signs just change, I get the answer of x equals -4 as a solution. If I check it, what I have is 2 to the opposite of, and then we replace x with -4, we get that notation. So that's going to be 2 to the 4th equals 16. And notice that does check out because we said 2 to the 4th does equal 16. So if I have 1/2 to the x equals 1/8, how do we solve this for x? The catch is if I can make the bases the same, then we're kind of home free. And again, 2 looks fairly friendly with an 8. So what we're allowed to do is we can keep this 1/2 to the x. But what I can do is I could change 8 to like 1/2 to the 3rd power. So because 1/2 times 1/2 is 1/8. So I can change this 1/8 using exponents 1/2 to the 3rd power. And since I have the bases the same, I can just set the exponents equal to each other and x equals 3. Well, that's solved. We're done with that. No more to do. So if I have 3 to the x squared plus 4x equals 3 to the 5th. Notice how the bases are the same here, so we don't have to deal with that, but we do have some strange looking exponents. But we are allowed to set those exponents equal to each other. And this becomes what we call a quadratic equation. To solve a quadratic equation, we can't solve for x, but what we can do is set this to 0 and use factoring as a strategy. So we know that to make this 0, if I could change this into a multiplication problem, that'll help us out. So I can use factoring to change this into a multiplication problem. X squared, there's really only one choice, x times x. That gives you x squared. But the other catch is this -5 has to add up to give me this 4. So the factors of a -5 have to add up to give me this 4. So we have to pass those two tests. Well, 5 only has two factors, 1 and 5. So that's easy. It has only those pair. And it looks like to get a +4, the -1 would have to be present. So -1 times 5 does give me -5. And -1 plus 5 does give me 4. So it does check out. So I put a -1 here and a +5 here, and we set that equal to 0. So using the multiplication property of 0, what makes this 0 would be 1. So x would equal 1. What would make this 0 would be -5. So I can just go ahead and just go straight to that spot. So this actually has two solutions, 1 or -5. They would both work. So if I look at this next example, I have 9 to the -x plus 15 equals 27 to the x. Notice that the bases aren't the same, so we're kind of in a spot here. So the catch is I'm trying to make these bases the same. Well, 9 and 27, that 3 seems to be the number that could be used. I can change 9 to 3 squared, but remember, that's still raised to the -x plus 15. On the right-hand side, I could change this 27 to 3 to the power of 3. But remember, that's still raised to the power of x. And notice how we have the power rule involved here. Notice how we have a power to a power. If we have a power to a power, we're allowed to multiply those exponents together. So this becomes in 3 times -2x plus 30. And on the right-hand side, we have, again, the power rule, 3 to the power of x. So we multiply those together, and that would give us 3 to the 3x. So from here, since we do now have the bases the same, we can set the exponents equal to each other to find what x is. So I have -2x plus 30 is equal to 3x. So now we have this equation that's linear. Since it's linear, our goal is to get x by itself. To get x by itself, we can't simplify either side. They're already simplified, but I can get the variable on one side. I usually pick on the little guy. So I'm going to make the -2x disappear by adding a 2x here, but also I have to add a 2x over there. So that's going to give me then 30 equals then this 5x when I do that math. Can't show it since I'm kind of running out of room. And then to make this coefficient turn into 1, I have to divide both sides by 5. So 30 divided by 5 is 6. And that gives me x equals 6 as a solution. So we are able to solve that one by using the same base there. This one also looks kind of strange to start with, but the catch is, notice that the bases are different. Since the bases are different, we're trying to create the same base. And it looks like that 3 is the one that is useful to us. So again, I'm going to use that 3 to the power of 2 to create the 9. That's still raised to the power of x. Times, and this already has a base of 3, so we don't have to change that. That just stays as is. But that 27, we're going to change to 3 to the power of 3, since that does represent 27, and that's raised to a power of 4. So using the power rule, again, I can multiply those exponents together. 3 to the 2x times 3 to the 4x equals 3 to the power of 12. So I have the power rule for this part here, and I have the power rule for over here. So that's cleaned up a little bit. Notice so here I have the product rule involved. Notice how I'm multiplying with the same basis. So I'm allowed to add the exponents in that situation. So this becomes 3 to the 6x equals 3 to the 12th. So I have achieved what I wanted to. I was able to set each side equal with the same base. So then I'll have to set the exponents equal to each other. So 6x equals this 12. And then that's a pretty easy equation to solve. We should have x equals 2 as a solution. We can divide both sides by 6 if we need to. So one last example. if we have e to the 3x equals e to the 5x minus 12, how do we solve this? Well, notice that they both have the same base. They're both e's. So since the bases are the same, all we have to do is use the logic of the exponents have to be equal. So I can just go straight to saying, well, 3x equals 5x minus 12. So again, if I pick on the little guy, I'm going to subtract 3x on both sides. So that becomes then 0 equals this 2x minus 12. Again, I can add 12 to both sides. Got some space here so I can show some work. So 12 equals then this 2x. Then if I divide both sides by 2, we end up with x equals, or 6 equals x, or x equals 6. So we were able to solve that for an answer. So that completes our lesson on working with exponential functions.